Okay, welcome back. Next we have Urtecho of NASA JPL and the California Institute of Technology. Dust devils on Mars could be a big problem for current and future missions to the planet, but Lewis is going to explain how dust devils here on Earth could possibly help us out. So, thanks, Lewis.
Thank you very much. Over the past year, I've been working on a joint project with NASA JPL and Sandia National Laboratories in developing a detection scheme for dust devils in time pressure signals. So, first of all, how do dust devils come about? They're a result of cold and warm air interacting with each other and in sort of sparsely vegetated environments. Dust devils have a notable dip in pressure near their centers, and this is what we pick up on our time pressure sensors. Dust loading itself plays a very big role in Martian atmospheric dynamics. It influences the albedo and weather patterns in specific regions. And for our eventual missions to Mars, dust can play a big role in wind erosion, and it could erode possible biosignatures that we could find and preserve in rock. And dust devils could also affect the longevity of missions. So here we have a picture of Mars InSight, a lander that was affected by dust loading. So on the first selfie, you can see there's basically no dust at all, but on the second selfie, dust is covering the entire lander. And eventually, InSight had to be decommissioned because it wasn't receiving enough power through its solar panels. Other missions include Spirit and Opportunity, whose lives were extended as a result of dust devils sort of cleaning off their solar panels. So moving on, what are challenges that we're facing in studying dust devils? Right now there's a lack of an in-depth record of dust devils, so this poses a really big problem because dust devils are a significant player in the Martian atmosphere. On Mars specifically, there is a very low station density. There are only a handful of rovers or landers. So we need to find a way that we can develop an effective analog to study dust devils on Earth and then sort of extrapolate our results to Mars. On this figure on the right, we can see dust devil density versus perceived survey area. So as survey area increases, the dust devil density, or the perceived dust devil density, decreases. This is just a result of larger survey areas only being able to pick up larger dust devils, and so the smaller dust devils are pretty much overlooked. And so the goal with our study is to sort of deviate from this trend line that we see here and be able to have a high station or a high area along with a high dust devil density. So this is our analog study. We recently have made available to us a 7-year deployment of seismometers and infrasound microbarometers at the Nevada National Security Site in the Mojave Desert. So it consists of 32 microbarometers, 20 broadband seismometers, and 100 geophones. So it's a lot of data, up to 10 to the 4th station days of data. So we're going to need to find a way to sift through all of this data to pick out dust devils and learn about formation characteristics. The unique landscape of the Nevada National Security Site sort of lends itself to a Martian analog. There's sparse vegetation and it's a pretty arid climate. And scaling from Earth to Mars is performed using background pressure and temperatures that we find from weather stations. So while the ambient conditions at Mars are different from those at the Nevada National Security Site, physical models for convective vortices suggest simple scaling relations that permit meaningful comparisons between the two. So here's another view of the stations that we have. So how do we make up our detector? It's a 2-part detector. The first is a wavelet detector. So with a wavelet detector, the goal is to detect energy peaks in the frequency domain. We do this using ambient noise models that statistically characterize signals that are more likely than not to be noise. So again, the wavelet detector is not as sensitive to noise when compared with the correlation detector, but it is pretty expensive. And then it's sort of agnostic to the signal. So it's able to pick out peaks in energy, but it's not able to sort of choose whether it's a dust devil or just some other signal that's being picked up. The other part is our correlation detector. The correlation detector sifts through these time windows that the wavelet detector picks out, and effectively it uses templates and overlays them on these time pressure series. And any section of the time pressure series that matches with a template is flagged as detection. And the pressure time series of dust devils are especially great candidates because, as we can see here, they sort of have an EKG-like signal. So it dips and then it goes back up again. And that makes it an excellent candidate for a correlation detector. Our plan is to eventually implement a joint detector so we can get the best of both worlds with each type of detector. So for our testing methodology and testing the efficiency of our dust devil detectors, we developed 10,000 6-hour-long synthetics with a random number of non-overlapping dust devils inserted at random points. Here we see an example synthetic. These dust devils have a range of pressure dips and time durations, and there are unique background noise parameters for each time pressure series. So again, this is used to test the recall and efficiency analysis of our detector. And the results of this were pretty promising. So we ran it again on 10,000 synthetics, and what we found was that with the wavelet detector itself, about 95% of dust devils were detected. With the correlation detector itself, about 83% of dust devils were detected. But joined together with the benefits of each type of detector, we were able to pick out 91% of dust devils with 99% precision. And so we can see up here in the chart on the upper right sort of the trade-off that we have between the two. With the wavelet, we have more recall efficiency but less precision, and the correlation detector vice versa. And then we eventually also ran our results on a subset of the catalog that we have had made available to us, and we picked out about 6,000 detections in total. We have yet to run the correlation detector on these detections. So for future work, we're planning on generating a full catalog for the 7 years of data that we've had available to us, and we plan to perform an analysis on the formation and dynamics of a large N data set of dust devils, and then eventually release a catalog of these dust devils and extrapolate our results to Mars based on atmospheric scaling relations. Thank you very much.
Great. Awesome. Thanks, Louis. I will go ahead and kick us off with a question. So you have this data from the Mojave Desert with these sensors that you showed us that were out there. How difficult would it be to gather that same kind of data for Mars?
So like I mentioned earlier, Mars has relatively low station density compared to Earth. There are only a handful of rovers and landers that are equipped with pressure sensors. So that's what makes this data set extremely unique, is that it's a lot of sort of infrasound microbarometers and seismometers and stuff. So this gives us a very unique opportunity in being able to learn more about dust devils.
And it looks like we have some questions from the room.
I have a lot of questions, but I'll settle on one. When you have a misdetection in either your wavelet or your correlator one, do you know if it's like a small dust devil versus a large one? Do you have a size?
Yes. Yeah, I had so many different figures I wanted to throw into this, but I just had a limited amount of time. But what we found was that with dust devils that are long in length, so we call it like a long full width half maximum, we have trouble detecting those, and also low dips we have detecting. So a low dip in pressure would be around like 3 to 5 pascals is sort of where we have trouble detecting dust devils. And those are synthetic dust devils. But in real life, dust devils range anywhere from like 10 to 100 pascal dips. So our dust devil detector is able to pick up most sort of observational data.
Can I ask one more? You're using pascals, right? So we're talking pressure, like raw absolute pressure units. On Earth, you said 10 to 12 pascals, so about twice as big as, you know, the threshold that your synthetic one is working at. How many, relative to that, what are dips on the Martian surface?
I can't say with certainty. I'm going to say that dust devils on Mars and on Earth are extremely equivalent. From the research that we've seen in the past, since sort of the station density and just the observations are so sparse, we're not able to make definitive sort of categorizations of dust devils. So I can't really say sort of the difference between the two of them.
So, Earth and Mars have very different atmospheres, and I'm curious, how big do the dust devils actually get on Mars, and how big do they have to be before we care, before they start messing with something NASA puts up there?
Well, okay. In reading through a bunch of papers preparing for this, I came across this one crazy dust devil that we recorded once. Dust devils on Mars have been recorded to get up to 1.6 kilometers in diameter. So that's pretty important, I would say. And again, on Mars itself, dust devils actually play a pretty large role in the atmosphere. They're about one dust devil for every square kilometer. So with a relatively high density, this could very obviously sort of affect future missions.